Hello, I am Montana State University chemistry teaching professor, Dr. Bill McLaughlin. Let's take a closer look into the chemistry behind fire. In Montana, fire is something we both enjoy and fear. As we head into summer, though, knowing a bit about the chemistry behind fire can help us ask better questions. First, let's take a peek into the life of scientists who study fire as a career.
We have years and years and decades, centuries of experience with fire. And one of the problems we have in general as humans is that we tend to think that because we experience something, we understand it. And that's not really true.
With fire, almost everything is counterintuitive. What appears to be intuitive is actually wrong. So my name is Mark Finney, and I'm a research forester here with the Missoula Fire Sciences Lab. The Fire Sciences Lab was built in 1960 for the purposes of understanding fire. You know, the figures for the federal government right now, we spend upwards of $3 billion a year dealing with wildland fire. We burn on average about 4 million acres a year. And it seems like the amount of area and the impact of these fires just keeps going up. We are not getting rid of fire. And so we need now to understand a lot more about it. You know, the goal of our research is to reverse engineer spreading fires.
Well, in order to understand more, let's go back in history with some early ideas, and then we'll travel back up to present times to explore what's going on. In early human cultures, people tried to figure out how everything worked and what everything was made of. Looking around, they noticed that some things were wet, some were dry, some hot, some cold, some solid, and others were gas-like. Well, their logic was that at the basis of everything going on, there must be simple components that mix together to produce what they saw. Well, to keep this idea useful, but as simple as possible, they produced an idea that lasted quite a long time. That idea was that various mixtures of the basic elements of earth, wind, water, and fire could explain everything. For example, if heat from fire was added to water, it could become part of the air as it changed from liquid to gas. Well, here's a diagram that summarizes the early plan of the 4 elements of nature. The early philosophers and scientists didn't really do much experimentation. They really just used logic and careful thought. For example, can you think of something that is made of smaller parts that when combined make a larger object? You might think of a brick wall of a school that looks smooth from a distance, but up close you can see it's made of lots of individual smaller blocks. You could look at a pile of snow and it looks solid, but you know that it's made up of really smaller individual snowflakes. Well, eventually, this idea of the elements from the philosophers was found to be too simple. Other scientists began to keep the basic idea, though, that objects were made of smaller pieces. About 200 years ago, those smaller pieces became known as atoms. It was found that a pure object, say a piece of solid copper or gold, was made of a certain type of atom. If it was placed in fire, for copper example, it would become black. This meant that the atoms could be made to combine with other different atoms. Well, today, chemists still use that ancient Greek term element, but we mean something different. An element is considered to be a substance made up of one type of identifiable atom. For example, carbon is an element made up of carbon atoms. Oxygen is an element, again, made up of oxygen atoms. We have identified over the past 200 years about 118 different elements from which every physical object is made. This, of course, would include wood, people, stars, really everything. Here's an example of the chart we use today. You can see it's quite a change from those earlier 4-element examples. Of course, there are more important details here. You may already know that atoms are made up of 3 even smaller particles known as electrons, protons, and neutrons. The atoms of each element have specific but different numbers of those particles, and that gives them their unique identities. All of this is helpful as we're going to explore the basic nature of fire. Well, although early cave dwellers likely did not state it like this diagram, they did know how to make a fire. Producing fire needs 3 requirements. There are various types of fuels, or substances that are flammable, but commonly the fuel has plenty of the element carbon combined with a few other elements. Without air, especially oxygen, there'd be no fire. Finally, the third component, heat, is necessary to get that fuel and air to begin to react. So when you watch a campfire, you're seeing the evidence of the 3 components coming together in an efficient way to produce heat and light. Just setting some wood out in the air, fortunately, does not cause a fire to develop. A small spark is needed to get the reaction, and then the fire to begin. In many forest fires, that spark can come from the energy of lightning. Heat and light are both forms of energy. Energy is not being made in a fire. It is just changing forms from the energy stored in the atom components of the wood and the oxygen to the new forms of heat and light. It's a conversion. How does this change or conversion happen? Well, stay tuned. We'll get to that in just a bit. Before that, though, let's take a look at that energy. Energy can be defined as the force that creates movement. What energy can do? Well, it's obvious. When you pedal a bike, you're using energy to power the movement of you and the bike. When you turn on a light, you're using electrical energy to convert to light energy. Even when you digest lunch, you're getting energy from the food to keep you warm and perform other body functions. Well, the list goes on, but in each case, we're just changing energy from one form to another form. For example, where does a hummingbird get the energy to so rapidly flap its wings 70 times per second? Well, it comes from the sugar molecules in nectar. They're reacting and giving the hummingbird their stored energy so it can quickly move its wings. Well, what is it, though, as we get right to it, about carbon and oxygen combining that releases energy? A good way to remember this is that chemical changes are atomic exchanges. Chemical changes are atomic exchanges. Today, we can identify about 118 chemical elements. Each element is made up of atoms with unique properties. You likely already know that atoms have specific numbers of electrons, protons, and neutrons, as we mentioned earlier. For example, most atoms of carbon have 6 protons, 6 neutrons, and 6 electrons. Well, potassium atoms are made up of 19 protons, 19 electrons, and 20 neutrons. Our modern element chart is so much more complicated than the simple 4 elements of the ancient times. The energy changes we detect when we see a campfire, heat, light, sometimes sound, all come about when the molecules in wood are changed into 2 new molecules. As a sapling, trees absorb energy from the sun in the photosynthesis process. The energy from the sun is then stored within the attachments between atoms as they make molecules. This means those molecules, mostly with lots of carbon atoms in the wood, are high energy compounds. They've absorbed energy from the sun. Well, when those high energy molecules combine with oxygen, 2 atoms of oxygen exist combined to make that O2 molecule. They will form new, lower energy molecules of carbon dioxide and water. This means that their stored energy is released as fire. In a fire, you are seeing high energy content molecules get rearranged to make new, low energy molecules. You're going from high energy molecules down to low energy molecules. So getting a campfire started though, we typically use a match, some heat source. Now when the chemicals in the match head get ignited with oxygen, they also release energy. If there is some easy to burn material nearer the fire, the match gets the other material burning also. As long as more energy is released in that process, the wood begins to ignite, which releases more energy, so even more wood begins to ignite, which releases even more energy, and so on. When you view a campfire, really or any fire, you're seeing a chemical, actually several chemical reactions. The chemical change, where original material is changed to a new material, releases several forms of energy. Now remember, once again, to emphasize, energy is not created in this process, it's stored and then it changes forms. In this case, it's released from the stored potential energy to become heat and light that we see in a fire. So this tells a short story about changing some molecules into new molecules by rearranging their atoms and releasing energy. Chemists have developed another way to tell the story. Chemical symbols can tell a story. Shown here is a balanced chemical reaction that is important in making a fire. Note that if you counted the atoms on the left side of the arrow, they would equal exactly the type and number of atoms on the right side of the arrow. They must. The carbon-containing compound on the left is, in this case, known as propane. You may have heard of propane being used as a heating fuel. The balanced chemical equation tells us that 1 unit of propane actually requires 5 units of oxygen to react. Further, the products on the right contain less energy stored in their atomic arrangements, so they'll form 3 units of carbon dioxide and 4 units of water. The larger numbers in front of the molecules are called coefficients. And when you see a coefficient, that multiplies all the numbers of the atoms following them. For example, 4 H2O would tell us, if you multiplied 4 by everything after it, that there are 8 atoms of hydrogen and 4 atoms of oxygen present. Just to check, do you see that on the left, propane contains 8 atoms of hydrogen? It should be balanced. In a sample of wood, there are many molecules that have carbon connected to other atoms that can be made to react with oxygen. And like propane, they produce a lot of carbon dioxide and water when they react. It turns out that carbon dioxide and water are stable, low-energy compounds. So, let's go through the reasoning about making fire once more. If high-energy carbon compounds in wood can be made to react with oxygen in the air, now remember, you still need a spark or some energy source to get it going, but the result will be these low-energy compounds like carbon dioxide and water. The change in energy is released as heat and light, or what we call fire. Well, what gives a campfire its typical red, orange, yellow color? How hot is a campfire? Well, first, campfires, although pleasant to look at, can be very dangerous. As Montanans who've experienced wildfires and the smoke that comes with them, we know this. The red coals within a campfire can reach temperatures very high, over 1,000 degrees Fahrenheit. The yellow portion, maybe even hotter. Always keep your distance, always. Some metals even begin to melt at those temperatures. To compare, water boils at 212 degrees Fahrenheit. So campfires are much hotter. When atoms become heated through their outer electrons can absorb that energy and enter what we call an excited state. These states are unstable and don't last very long. The excited electron, though, returns to its normal state by giving off the absorbed energy as light. Different atoms, when excited and relaxed, give off different colors of light depending on the atoms present. For example, atoms of potassium give off a light purple color. Potassium is found in some compounds in woods, and you can see that sort of lilac color. Excited calcium atoms can produce red color. Sodium compounds, also found in wood, produce a slightly yellow to orange color. Campfires do not produce much blue light. That type of electron excitement actually requires higher temperatures. So from candles to campfires and even forest fires, you are seeing a process that combines fuel with oxygen. These are commonly called combustion reactions. You may wonder that since water is often a typical product of combustion, how the fire survives in all that water. Remember, all this is very hot. Water at these temperatures will not be a liquid. Rather, the water present will be in its gas form, so not very useful for putting out a fire. The expanding water also helps open up wood to expose more fuel to the air for combustion. Sometimes that pop you might hear in the wood is partially caused by the pressure from hot water that's going to the gas form. So, do you think you could explain all this to someone else? The next time you're around a campfire with family or friends, teach them some chemistry.